Welcome to video show from the desk of Shailesh Kadakia, founder, Matrix Writers and Publishers LLC. This video is about famous Collatz Conjecture, which is about a pattern of shrinking numbers created by set of rules. The conjecture requires you to start picking a number either even or odd. If the number is even, perform step A, where you repeatedly divide the number till you end up in an odd number. If the number is odd, you multiply that number by 3 and add 1 and then divide by 2. Once you complete step B for odd number, if the result is an even number, go to step A. If the result is odd number, go to step B and repeat this process. It has been validated that for both even and odd number selected, the final sequence after performing repetition of steps A and B would result in pattern 8421. This conjecture was unsolved for past 300 years. Mr. Kadakia taken to provide proof of this conjecture by empirical method of analyzing pattern developed during the course of execution of steps A and B. The conjecture states that repeated execution of steps A and B results in a shrinking pattern 8421 and no other pattern occurs. So part A of the conjecture requires to prove that execution of sequence steps A results in a shrinking pattern, and second part of the conjecture requires you to prove that the pattern, only pattern that occurs is 8421. A formal proof of the conjecture did not exist. So we will focus on results upon repeat execution of steps A and B for two possible scenarios where the starting number selected is even or odd. Now, if the starting number is even, we repeatedly execute step A divided by 2 until we reach an odd number. So at the end of repeated execution of step A, find that the starting number is reduced by a factor half raised to k, where k is the iteration count that the number is divided. When we find an odd number, we perform step B. In step B, we will multiply that odd number by 3 and add 1. Because when you add two odd numbers, 3n plus 1, you will always get an even number. Therefore, in step B, we divide immediately by 2. Now, when you divide number 3 times n plus 1 divide by 2, you can get either odd or even number, depending on n is even or odd. And we perform repeated execution, but at the end of step B, we will make the number small by factor 3 over 2. Actually, we will magnify the factor 3 over 2 raised to the power L, where L is the repetition of step B. So, if we combine the step A and B for an even number, the final resultant number will be 3 to the power L divided by 2 to the power K plus L. But 3 to the power L over 2 to the power K plus L is less than 1 for K greater than 1. Therefore, the starting number, if it is even, it will become small by factor of 1.5 raised to L over 2 raised to K, which is always less than 1. So number pattern eventual will be always a strand. So we have proven first part of the conjecture, because even if you begin with odd number, this time you will perform repeated execution of step B first and repeated execution of step A. But at the end result will be the same. That will be, the number will be reduced by factor of 3 raised to L over 2 raised to L. Again less than 1 for K greater than L. Now, to prove the second part of the conjecture, that the only sequence that can occur is 4 to 1, closer examination of odd number sequence is required. And here is the reason why we state that we have to inspect odd number repeated execution closer than even. Because throughout the number line, there are perfect powers of 2. They are embedded. The numbers that are exact multiples of powers of 2 are called perfect powers of 2, such as 512, which is equal to 2 to the power 9. So these numbers, whenever we run into during execution of either step A or B, we will end in the shrinking sequence of numbers 8, 4, 2, 1, because we will execute step A repeatedly non-stop, because the number is a perfect power of 2. So during execution of either step A or B, if we run into these even numbers, we will definitely end up into sequence 8, 4, 2, 1. So that part we have solved, that when number is even, we will run into a number that is exact multiple of powers of 2, and we will end up having sequence 8, 4, 2, 1. Now let us examine the number pattern generated when we start with number odd and we perform step B repeatedly. Now, in odd number n, it can be expressed as 2m plus 1, where m is even or odd number. Now, if we substitute n equals 2m plus 1 in step B, because we are multiplying the starting odd number by 3 and adding 1, we will multiply 3 times 2m plus 1 and add 1. So that will become 6m plus 4. So in the first part of step B, when we multiply odd number, we will generate a number 6m plus 4, and that will be always even. And when we divide that number by 2 according to the second part of the step B, we will get a number which is 3m plus 2. Now 3m plus 2 number can be either even or odd. And depending on whether 3m plus 2 is odd or even, we will repeat the steps of conjecture A or B. Now, to prove that when the number is odd, also we will end up sequence 8421. We will closely examine the pattern of numbers created by 3m plus 2 by substituting value of m, even and odd numbers. We find that the sequence of numbers, it will start with 5, it will increase by 3. So it is 5, 8, 11, 14, 17, 20, 23, 26, 20, so on and so forth. So when the numbers are in this pattern, we can examine that the pattern generated by numbers 3m plus 2, they cannot be divisible by 3, because if you divide 3m plus 2 by 3, you get number m plus 2 over 3, which is not a whole number. Therefore, repeated execution of step B can never produce a number sequence which are multiples of 3, such as 81, 27, 9, 3 and 1. So we have proven that even if we repeatedly execute step B, we can never get numbers that end with 81, 27, 9, 3 and 1. Now let us also examine why the number doesn't end up as a multiple of 5, such as 20, 10, 5, etc. The reason is that if we look at the pattern generated by 3m plus 2, 5 is also, 5 can produce a whole number multiple. So 3m plus 2 can produce a whole number multiples of 5. But because the numbers are shrinking, any multiple of 5 such as 20, 30, 40, 50, 60, this will become reduced. When you divide by 2, it will end up becoming 5. But as soon as it becomes 5, when you multiply by 3 and add 1, 5 times 3 is 15 plus 1 is 16. So as soon as you reach the smallest number 5 as a multiple of 5 generated from 3m plus 2, you get 16 and you end up executing even numbers according to step A, and that will produce 8421. So yes, 3m plus 2 sequence contains exact multiples of 5, but because multiples of 5 includes numbers that ends with multiples of 10, so we always end up generating pattern 8421 even if 3m plus 2, the step B, produces a pattern of numbers such as 80, 40, 20, 10 and 5. Now let us prove that there are no other prime number patterns that can be generated when we are executing step B repeatedly, because we encounter odd numbers continuously. The reason is that when you perform repeated execution of step B, when you encounter odd number from 3m plus 2, the examination of pattern sequence generated by 3m plus 2 reveals that any multiples of higher prime numbers, they occur in what I call as a skipped sequence. So you have like numbers 5, 8, 11, 14, 17, 20, 23. So you can see that after 14, in 3m plus 2 sequence, 20 doesn't occur. So when you perform the loop of step B, you cannot continuously generate the number that is exact multiple of 7. And therefore, you cannot have a shrinking sequence of numbers that are multiple of 7. The same argument holds good for higher prime numbers, because 3 times m plus 2 can never generate a whole number if you divide it by higher prime numbers such as 7, 11, 13, 19, 23, 29. So for any size larger than 5, other prime numbers cannot occur in repeated sequence when you perform step B and step A. Therefore, we have proved both parts of the conjecture, that only the final sequence that can occur is 8421. For more information on my proof, please download a file at the link specified at the end of the video and watch this YouTube. Thank you for your attention, and please give me thumbs up and visit my YouTube channel. If you have any questions, please email me and I will get back to you as soon as possible. Have a wonderful day. Bye-bye.